All right, let's talk about memes. Let me switch over to my notebook. Now, here's an old meme. Kilroy was here. This was a popular bit of graffiti in World War II. People would draw this little guy all over the place. You are, of course, almost certainly familiar with image macros, lolcats, and all those other things, but memes are not about cats, they're not about pictures, they're not about these jokes. Although those things would qualify as memes, really what they are is the unit of analysis for cultural evolution. Now, what do we mean by culture? Well, we mean a lot of things. Cultural evolution. Sorry, I can't spell and talk at the same time. So our culture is including a lot of different things, including language and cliches and all kinds of stuff. Of course, the economy we could think of as a part of our culture. So it's a very broad term, but this unit of analysis is kind of a tricky thing. We'll delve into that in a little bit in this video, but let's start with a little bit more context. So we're thinking about, in this class, of course, the internet, the economy more broadly, right, or any particular economy or any particular market we can think of as some aspect, some part of culture that's facing evolutionary forces. And these things we can categorize, here's another little bit of jargon, as complex adaptive systems. Now, this idea of complexity is really interesting. So we might distinguish this from a related word, complicated. So if I think about what's going on inside my car engine, that is a complicated system. If I think about what's going on in an ant colony, that is a complex system. So the ants are, well, I was going to say relatively simple, but of course they're incredibly intricate. They got a bajillion genes, there's all these moving parts, but any given ant on its own is pretty simple, right? Simple enough, but the hive, the colony as a whole, has all these little interactions between those simple components that results in something that is different than the whole. We'll talk more about this idea when we get to the emergence module. Now, when we're thinking about complex adaptive systems, we can understand them, but we're going to have a difficult time predicting them. So what we want to do with this, with any of these, is we want to think about what are the component parts. And we're going to see that memes are sort of a broad label for the component parts of all sorts of cultural systems. So we want to understand the components. We want to understand how they work individually. We want to think about their interactions, right? So if we think about, say, the economy or a market, we're thinking about individual buyers and sellers buying and selling stuff, right? So those interactions and the people doing those interactions collectively creates what the economy is. So that's something where by looking at those things, we can understand, but as I said, it's going to be really hard to predict. In fact, in some cases, it's going to be impossible to predict. Now, a previous version of this class, I used to use the book Complexity, I believe it's Complexity and Introduction by Melanie Mitchell, which is a really excellent book and I highly recommend. She delves into a lot of the technical details behind this, including the basic idea of what's going on with chaos theory. And chaos theory is an intimidating sounding thing, but really it's a simple idea, which is some systems are incredibly sensitive to initial conditions. So I won't talk about it here, but go ahead and look up the butterfly effect. And that'll give you some idea of why it's hard to predict these complex adaptive systems. So in the case of the weather, the story is the flapping of a butterfly's wing, if unaccounted for, could dramatically mislead very complex and complicated weather models. But more broadly, it just means that when you go far enough out, little tiny things can compound. We'll talk a little bit later also, kind of related idea of power law distributions, which is basically just situations where instead of things sort of adding and subtracting so that you kind of end up with some normal type of distribution, with a power law distribution, things multiply and divide, so you end up with a very different sort of distribution. Now let me go to another related concept. I'll share on my screen. This will be a little easier to see. This is Stephen Wolfram's book, A New Kind of Science, which you can access online for $0. It's a really interesting study. He's trying to put together sort of a big theory of everything. And he uses as his simple example a cellular automata system. So cellular automata, this isn't something you really need to worry too much about, but it's just a really simple system where you've got these different blocks that respond to each other in particular ways. There are several cellular automata systems, but my favorite is probably Conway's Game of Life, which you should also look up. This is an incredibly cool thing. So Conway's Game of Life is a two-dimensional cellular automaton, where each individual block, each individual cell is either on or off based on particular rules. And based on these really simple rules, you can end up with incredibly complex outcomes. Maybe I'll share some examples of that on the class Discord later. So Stephen Wolfram and other people studying complexity have tried to categorize what sorts of outcomes can we expect. So we might be thinking about, what do businesses do? How do they evolve over time? How do their actions change over time? How does society, how does culture, how do all these different things change over time? Well, it's a big complex thing, right? We've got history departments talking about this, philosophy, sociology, econ. There's a ton of stuff, a ton of detail. So looking at a cellular automata lets you strip away a lot of that detail. And when you look at a cellular automaton, you get these four basic types of outcomes. So these are just four specific examples. So class one outcome, class one category of how a system might evolve, what it might evolve towards. In this case, it goes to sort of one steady state. So the universe as a whole is a system with entropy, and a bajillion years from now, eventually we get the heat death of the universe. So on a very large scale, the universe is going to go all black, like this particular class one cellular automaton. So he's got different rules, and you can look this stuff up, but this is, I guess, rule 250. So you start with a row of cells up along the top, and then as you go down, you're looking at how it's progressing through time. So these rules might look like you look at the cell to the left of you, look at the cell to the right of you, and if either one is on, then you turn black, right, in this case. And if you have rules like that, it's going to be pretty quick to end up with all of the cells turn black. That's kind of a boring outcome, right? No big deal, but that is something that happens. That is sort of one way we might think about how things turn out. You also have another kind of boring, maybe not boring, but a very interesting thing, an oscillator, which you've probably already read a little bit about in our 6 Degrees book, a system that kind of goes back and forth between a set of different outcomes. A really neat, well, how far a digression do I want to go? I'll just leave a note about the logistic function. I want to give you ideas of things that are neat to look up, but they're not terribly urgent. We don't have a ton of time, so maybe you just save these, find them on YouTube and put them into your save to watch later playlist. But a class 2 outcome, it's something that just oscillates. It just goes back and forth, right? So it's still more complex than class 1, but it's still kind of boring. Class 3 is kind of random. Right? It's random in the sense that economists use the word random, or mathematicians use the word random. So we can see here with class 3, we get these patterns which are really interesting. But if we wanted to say, think about what is this system going to look like after however many rounds, right? So what do we do? I'm trying to read this code, but I don't actually know Wolfram language. So I think 75, class 1, oh, whatever. Let's just say this goes on for 100 rounds. If we want to know what's going to happen to some class 3 system after 100 rounds, in this case, we might say, well, it's going to be like 50% on, 50% off, or 67% on, or something like that. We can kind of make an aggregate prediction. We don't know what's going to happen in any particular column, right? So what's going to happen to this particular cell after 100 rounds? It's going to be black or white, and there's going to be some chance that it's black. So we can describe it, but it's something where we can kind of understand the average because it's effectively random and chaotic. Class 4 is where things are a little bit more interesting. Here we're starting to see some real structure in this. So this particular example that Wolfram is giving us, we've got this situation where we're kind of seeing interesting patterns. We put in something and we're getting something out with some structure in it. And this is effectively what we're getting out of most complex adaptive systems that are interesting. Right? So the economy, it's not just that things turn out randomly. It's not that things just go back and forth in some boring old cycle. It's not the, what's the word I'm looking for? Not the word, Malthus. It's not this Malthusian system where we just run out of food and we're always on the edge of starvation. It's this interesting thing where we build these new things that you couldn't have predicted. You couldn't really anticipate that such a structure would come out of this system. So this system, our class 3 example, cellular automata 126, here we can say, oh, we're making some triangles and they're kind of randomly scattered around. Here we're getting these kind of elaborate structures that you couldn't anticipate from understanding what Rule 52 is. From Rule 52, let's take a quick look at that. So Wolfram Alpha will also run this. So here are the basic rules. You're looking at the cell in the middle. If it's on and its neighbors are on, it turns off. If it's on and its left neighbor is on, but its right neighbor is off, it turns off. So it's doing all these different things. You've got these 8 basic conditions that any individual cell might be in. And then based on that, for each cell, they're going to change what they do, and that's going to affect their neighbors. And the result is, if you give some random initial conditions, you're going to get some pattern. If we go back to this other example, which I should have saved to make this a little faster, you're going to get a different sort of an outcome. All right, so you can fiddle around with that stuff at your leisure. And again, the logistic function is a really interesting mathematical example of a deterministic function with chaotic behavior. It's something where, depending on the parameters, it looks like an oscillator. It oscillates between different things. But when you think of the system and the parameters overall, right, the sort of meta system, the logistic function turns into something really interestingly chaotic, something unpredictable, despite the fact that the inputs are deterministic. There's no randomness built in, and yet randomness emerges from it. That's a mathy thing. Don't worry too much about that. The big thing I want you to understand at this point is appreciating that the internet, the economy, the things that we're concerned with as economists are complex adaptive systems, and they're made out of these smaller components that we could categorize as memes. All right, I'm going to stop here and split up this video because I want you to stop and think about these things, look through your notes, look stuff up, and I've got a lot to say, or a lot more than I anticipated I wanted to say. So I'll put together a playlist. So stop, ponder on these things for a little bit. Think about, this notion of interacting simple components leading to a complex system. That's the name of the game when we're thinking about the economy. And then think about memes as something beyond just the internet jokes that we're all used to, although those are a useful way to think about this cultural evolution. Check out the website knowyourmeme.com, and you'll find some histories of some popular memes, and you'll see how they kind of change over time as people pass them back and forth between each other.